So picture this. You're sitting on a train.
Okay.
You've got your laptop open, and you're just grinding away on this massive collaborative design file for a really crucial project.
Right. Or maybe it's, a huge text document, something with 50 different moving parts.
Exactly. But as you know, if you've ever tried to actually be productive on public transit, the Wi-Fi is just an absolute disaster.
Oh, yeah. The blitz.
It drops out completely every time you enter a tunnel, right? It flickers back to life for maybe, I don't know, 3 minutes of really slow connectivity, and then it just vanishes again.
Yeah, you're basically working in these little isolated bursts.
Right. Now, picture your coworker. They are in another country entirely. Let's say they're sitting on an airplane, 30,000 feet over the Atlantic Ocean.
Okay, so they are completely offline.
Completely. Not a single bar of signal. And yet they have the exact same file open on their screen, and they are working.
They're making changes.
Yeah, moving images around, rewriting paragraphs, restructuring entire pages.
Yeah.
You are making your changes in your intermittent, flickering train tunnel reality.
Right.
And they are making their changes in their totally isolated airplane reality.
Yeah.
You are both completely siloed.
Which is, I mean, traditionally, that's a terrifying setup.
Oh, absolutely, because
Yeah.
then the inevitable happens, right? Your train pulls into the station, and your laptop instantly connects to this stable 5G network. And your coworker's plane lands on the tarmac, their phone connects to the local cellular tower, and you both hit the global internet at the exact same fraction of a millisecond.
Yeah, and in traditional computing, this is a nightmare scenario. I mean,
Yeah.
it is the specific catalyst that causes legacy systems to panic.
Just completely melt down.
Exactly. They lock up, or they completely overwrite one person's entire day of work.
But, and this is the crazy part, that doesn't happen anymore.
No, it doesn't.
If you're using modern tools like Figma or Google Docs, the server doesn't catch fire.
Right.
The document doesn't, spontaneously corrupt. It just seamlessly stitches those two totally divergent, isolated realities back together.
Yeah, you just see their changes materialize on your screen. They see yours, and the work just continues as if neither of you were ever offline.
It's wild when you really think about it.
It is a profound paradigm shift, and
Yeah.
it feels so natural to us now that we kind of forget what a mathematical miracle it actually is.
A miracle to reconcile two completely different versions of history, right? Without any human intervention.
Exactly.
I was actually thinking about the old way we used to handle this, like back in the early 2000s.
Oh, the file locking days.
Yes. The philosophy was basically just file locking. It was the digital equivalent of checking a physical book out of a library.
Right. If I have the book, you cannot read it.
Exactly. If I was editing a spreadsheet on a shared network drive, a little prompt would literally pop up on your screen saying, file is locked for editing by another user.
Yeah, we traded collaboration for safety because the underlying architecture simply could not handle the friction of two people talking at once.
Right. And then when we finally decided, okay, we want multiple people typing at the same time, the initial solution was this concept called operational transformation.
Right. OT?
OT, yeah, which is what those early collaborative text editors relied on.
Yeah.
But from what I understand, OT was incredibly fragile.
Oh, incredibly. Because it required a central server to act as a dictator.
Okay, a dictator. How so?
Well, think about it. If you type the letter A at position 5 and I deleted position 4 at the exact same time, the central server had to catch both of those operations.
Right.
It had to do complex math to realize, oh, your A now actually needs to go at position 4 and then send the corrected operations back to us.
So the server basically had to play traffic cop for every single keystroke.
A highly stressed traffic cop, yeah. I mean, the code to make operational transformation work flawlessly at scale was notoriously complex.
I can imagine.
Engineers would have to write these endless edge case rules just to prevent the document from tearing itself apart.
Wow.
And crucially, going back to your scenario, if you were offline for hours on an airplane making thousands of changes.
Right, and then you just dump them all at once.
Exactly. If you tried to dump all those delayed operations onto the server at once, the OT system would frequently just collapse. It was too much to reconcile.
Which brings us to the actual mechanics of how modern apps survive that airplane scenario today.
Right.
When I was digging into the research for this deep dive, specifically the work compiled by developer Jake Lazaroff, the realization that really clicked for me was that modern collaborative apps have largely abandoned that dictator server model.
Completely.
They use a totally different approach called CRDTs, conflict-free replicated data types.
It's a mouthful.
It is a mouthful,
Oh.
but we are going to look under the hood of these structures today. And don't worry, no heavy academic jargon.
We'll keep it grounded.
Yeah, we just want to look at the surprisingly elegant algorithms that make real-time collaboration possible, because it's fascinating.
It really is. I mean, the term conflict-free replicated data type is dense, but the concept is remarkably resilient.
Okay, so break it down for us. What is it?
At its core, it is a specific data structure that lives independently on different computers, which in a network we call peers.
Right, peers.
The defining characteristic is that every single peer updates its own local state instantly.
Okay.
When you are on that train and you press a key, the letter appears on your screen right then. You are not asking a central server for permission.
So you're just changing your local reality.
Yes. And because everyone is updating locally, freely without checking in, the peers will absolutely have different states.
Because they're cut off.
Exactly. Your document is temporarily very different from your coworker's document, but the mathematical foundation of a CRDT guarantees something called eventual convergence.
Eventual convergence. I like that.
It means no matter how long you are offline, whether it's a 3-minute train tunnel or a 12-hour flight, the math ensures that once those computers finally communicate, they will perfectly align on a single shared state.
Eventual convergence is a great phrase, but I really want to understand how it actually achieves that alignment.
Right, the mechanics of it.
Yeah. Lazarov's work breaks this down into two distinct philosophies of syncing data, state-based and operation-based.
Yeah, the academic literature calls them CVRDTs for convergent and CMRDTs for commutative.
Let's stick with state-based and operation-based.
Good call. Because looking at them as state-based versus operation-based describe exactly what is traveling over the network wires.
Right. And to visualize this, I keep coming back to a blueprint.
Okay, a blueprint.
Yeah, imagine we are both architects working on the exact same house. With a state-based CRDT, every single time I move a chair in the living room, I take the entire massive blueprint of the whole house. I roll it up in a tube and I mail the whole thing to you. You look at it, merge it with yours, and we move forward.
Right, you're sending the whole state.
Exactly. But with the operation-based approach, I don't send the blueprint. I just send you a tiny text message saying, hey, move the living room chair 2 inches left.
That captures the core mechanical difference perfectly. State-based transmits the full, heavy reality. The peers receive these massive blueprints, and they run a merge function to synthesize them.
Okay.
Operation-based transmits only the highly specific actions. The peers receive the actions and calculate the new state themselves.
But looking at that dynamic, the state-based approach seems wildly inefficient.
It does seem that way, yeah.
I mean, if you and I are working on a massive gigabyte-sized design file, and I just fix one typo in a text box, mailing the entire gigabyte file across the internet for a single typo is a massive waste of bandwidth.
On paper, yes.
So why would system architects ever choose to send the whole blueprint when a 1 kilobyte text message does the job?
Well, it comes down to trusting the physical infrastructure of the internet.
Trusting the internet.
Yeah. The operation-based approach, the tiny text message, it is incredibly efficient for bandwidth, sure. But it places a crushing burden on the network itself. It demands a flawless communication channel.
Because the internet is fundamentally chaotic.
Extremely chaotic. Underneath the sleek apps we use, the internet is literally just packets of data being thrown across physical cables, bouncing between routers that are constantly failing, rebooting, or just getting overwhelmed.
Right. Things get lost.
Messages get dropped entirely. Packets take different physical routes across the ocean and they arrive out of order. Sometimes, a confused router will duplicate a packet and send you the exact same message 3 times.
Oh, wow. I see the vulnerability there.
Right.
If I send the operation, move the chair 2 inches left, and a network router panics and duplicates that message 5 times, your computer receives 5 identical instructions.
Exactly.
You move the chair 10 inches to the left. The chair is now embedded inside the wall.
And the architecture of the house is ruined. Or consider order of delivery. I send an operation saying, move the chair, and a minute later I send, paint the chair red. But because of how routing works across different internet nodes, the paint chair red packet arrives at your computer first.
Oh, so your system tries to paint a chair that it doesn't even know exists yet.
Right. It crashes. If you rely on operation-based CRDTs, you have to build incredibly complex, heavy infrastructure just to guarantee that messages are delivered exactly once and in strict causal order.
Which kind of defeats the whole purpose of making it lightweight in the first place.
Precisely.
Mm.
Which brings us back to the state-based approach. Yes, sending the entire blueprint is heavy, but it is bulletproof against network chaos.
Because it's the whole picture.
Right. If a router duplicates the massive blueprint and you receive it twice, it doesn't matter. You just look at the second identical blueprint and say, I already have this.
Okay, that makes sense.
And if an older blueprint arrives after a newer one, you can easily discard the old one. The blueprint contains the entire truth of the document, so it doesn't rely on a sequential history of actions.
It just is.
Exactly. Now, to be fair, there are hybrid approaches out there, often called Delta CRDTs, where peers negotiate to only send the tiny slices of the blueprint that change.
Right, like a diff.
Yeah. But for our purposes, focusing on the pure, bulletproof, state-based CRDT really reveals the core math of how these systems resolve conflicts.
Okay, so we are mailing full blueprints. We are firmly in the state-based world.
We are.
But that creates a massive logical hurdle. I mean, I have my blueprint where the chair is by the window. You have your blueprint where the chair is by the door. We swap blueprints.
Right.
How does the computer actually mash them together without destroying the house?
Right.
It has no human intuition. It doesn't know who is right.
It doesn't need intuition. It relies on 3 specific mathematical properties.
Okay.
But to understand how they apply, we first have to look at how a CRDT is actually built. It is divided into 3 distinct layers.
Yes, when I was looking at how Lazaroff models this,
Yeah.
the separation of those layers was really the key to understanding it for me. You have the value, the state, and the merge function.
Right, the triad. So the value is what you, the user, actually see on the screen.
The pixels, basically.
Exactly. It's the text of the paragraph, the hex code of the color, the coordinates of the image. The application rendering the interface only ever cares about the value.
But the value isn't what's actually being mailed back and forth in the blueprint.
No. What travels across the network is the state.
The state.
This is the hidden metadata. It is the invisible scaffolding that the computers use to negotiate with each other. The value is derived from the state, but the state contains the entire history of how that value came to be.
Got it. And then the third layer is the merge function. That's the engine.
That's the engine.
It takes my local state, ingests your incoming state, and combines them into a unified reality. And for a CRDT to work, that merge function cannot just be a random algorithm.
No, not at all.
It has to satisfy 3 unbreakable mathematical laws.
Right. Commutativity, associativity, and idempotence. I know. But if your merge function honors all 3, you are guaranteed to achieve eventual convergence, regardless of how badly the network mangles the delivery of the data.
Let's break those down into plain English,
Yeah.
because honestly, the math terms can be a little intimidating.
Fair enough.
The first one is commutativity. AORB equals BORA.
Right. It basically means the sequence of the merge does not matter.
Okay.
If you and I exchange our states, you can merge my data into yours, and I can merge your data into mine, and our computers will both spit out the exact same final document. The direction of the merge is entirely irrelevant.
Okay, that handles 2 people. But what if we have a massive team? That's the second one comes in, right? Associativity.
Yes.
If you have states A, B, and C, grouping doesn't matter. Merging A and B together first and then adding C results in the exact same state as merging B and C first and then adding A.
And this is vital for a peer-to-peer network.
Why is that?
Well, imagine you are offline on that airplane, and your team of 10 people are all working. When you finally land and reconnect, your computer is going to get hit with a flood of different states from different peers simultaneously.
Oh, right. A massive data dump.
Exactly. Because the merge is associative, your computer doesn't have to panic about, the optimal order to process them.
It doesn't have to queue them perfectly.
No. It can grab them in whatever random groupings they arrive in, merge them, and the final document will be mathematically perfect.
I want to pause on commutativity and associativity for a second, because Lazaroff points out a really fascinating trap here.
Oh, the floating point thing.
Yeah. We assume basic math always follows these rules, but in programming, it actually doesn't.
No, it is a brilliant constraint to highlight. He uses floating point arithmetic as the prime example of this trap.
Right, which is basically how JavaScript, the language of the web, handles decimals.
Exactly. Because computers have finite memory, they cannot store infinite decimal places.
Like pi.
Right, like pi. So when they perform calculations on tiny, tiny fractions, they eventually have to round off the numbers at the microscopic edges just to save space.
Okay.
And because of that forced rounding, the way you group the numbers actually changes the final result.
So wait, You're saying that 0.1 plus 0.2 grouped together plus 0.3
Yeah.
might equal something slightly different than 0.1 plus the group of 0.2 plus 0.3.
Inside the computer's memory. Yes.
Wow.
The difference might be at, like, the 15th decimal place, but in computer science, a difference is a difference. The hashes won't match. Therefore, floating point math is commutative. The order doesn't matter, but it is absolutely not associative.
That's wild. And the inverse is true for other math, too, like matrix multiplication, which is used heavily in rendering graphics on a screen.
Exactly. Matrix multiplication is associative. You can group the matrices however you want.
Right.
But it is completely non-commutative.
Right.
If you multiply matrix A by matrix B, you get a totally different result than multiplying matrix B by matrix A.
Which means if an engineer naively tried to build a CRDT merge function using just standard decimal math or matrix math, the system would silently fail.
Completely fail. Every time people merged, their documents would drift apart by these microscopic fractions until eventually the entire file was corrupt.
The math has to perfectly satisfy both rules, completely independent of how the programming language handles rounding.
Which brings us to the ultimate defense mechanism. The third rule, idempotence.
Idempotence. A-O-R-A equals A.
Yes.
Meaning merging a state with itself changes nothing. When I read this, the image that immediately came to mind was standing in a hotel lobby waiting for an elevator.
Okay, I like this. Go on.
So the system state you want to achieve is the elevator's coming to the ground floor.
Right.
You press the call button once, it lights up, the state is registered, but you're in a hurry, you're looking at your watch, so what do? You press the button 10 more times in a rapid-fire panic.
A very, very human reaction.
We've all done it, but pressing it 10 times doesn't summon 10 elevators.
Yeah.
It doesn't make the motor pull the car down 10 times faster. The end state, the elevator is in motion, remains completely identical whether you sent the signal once or 100 times. The action is idempotent.
That is a perfect analogy for network resilience.
Really?
Yeah, because remember that broken router we talked about, the one that sends you the exact same network packet 5 times in a row?
Oh, right.
If your merge function is idempotent, your computer processes the first packet, it updates the document, and when the next 4 identical packets arrive, it just shrugs.
It just ignores them.
Exactly.
Yeah.
Merging the same state infinitely yields the exact same result. It completely neutralizes the chaos of the internet.
So we have the theory. Commutativity, associativity, idempotence. Order doesn't matter, grouping doesn't matter, duplicates don't matter.
That's holy trinity.
But how do we build an actual application out of abstract math? I mean, according to the deep dive into Lazarov's models, everything starts with the absolute simplest primitive structure.
Right. The last right wins register.
The LWW register.
Yes. It is the atomic unit of a CRDT. A register is simply a container that holds a single solitary value.
Just one thing.
Just one thing. It'd be one letter, a number, a Boolean, true or false. Think of it like a smart light bulb that only knows on or off.
And the last right wins part is the conflict resolution strategy.
Exactly.
If 2 people try to flip that light bulb switch at the exact same time, the register uses a timestamp to determine who was chronologically last and simply overwrites the old reality with the new one.
Right. And let's look at the hidden state of this register, because remember, it doesn't just store the word on, it stores a tuple.
A tuple.
Yeah, a small package of 3 connected pieces of metadata.
The tuple is peer ID, timestamp, and the value itself.
Okay.
So if I turn the light on, my computer stores my unique ID, the exact time I did it, and the value on.
Perfect. And the merge function for this register is ruthlessly simple.
How simple?
When your computer receives an incoming state from me, it only looks at the timestamp. If my timestamp is smaller than yours, meaning my action happened in the past, your computer drops my update entirely.
Because your reality is newer.
Exactly.
And if your timestamp is larger, my computer basically surrenders.
Yeah.
It overwrites its local value with your value, adopts your newer timestamp, and records your peer ID as the last person to touch it.
And this is big, but this introduces one of the most notoriously difficult problems in distributed systems. We are relying entirely on timestamps to determine reality.
Right.
So what is time?
Okay, I actually got really hung up on this when I was reading, because my immediate thought was, why is this even a problem? Every laptop, every phone is connected to the internet. Just ping a global NTPE time server, get the exact millisecond from an atomic clock, and use that. We all have the exact same time.
We have the illusion of the exact same time.
Really?
In reality, perfectly synchronizing wall clocks, real-world time across a distributed global network is bound by the law of physics.
Because of the speed of light?
The speed of light and the physical distance of cables.
Okay.
By the time an atomic clock in Colorado transmits a signal saying it is exactly 12.00.0001, it takes 50 or 100 milliseconds for that signal to travel through fiber optic cables to a server in Tokyo.
Oh, wow.
By the time Tokyo receives the timestamp, it is already 50 milliseconds in the past.
So they can never be perfectly aligned.
Never perfectly.
Yeah.
And add to that the concept of clock drift.
Clock drift.
Yeah. A computer processor that is running incredibly hot, maybe rendering a massive video file, will actually have its internal hardware clock ticked slightly out of sync compared to a computer sitting idle in a cold room.
You're kidding.
No, they drift apart by milliseconds over hours.
But it means if I'm in New York and you're in Tokyo and
Yeah.
we both press a key at what we perceive to be the exact same nanosecond, our wall clocks might report timestamps that are 20 milliseconds apart.
Exactly.
And the system would give priority to the person whose clock drifted forward, not the person who actually typed last.
Which completely destroys the integrity of the document.
Yeah, that's terrible.
Wall clocks are practically useless for strict, deterministic conflict resolution, so engineers abandon real-time entirely. They use logical clocks.
A logical clock. Okay, so instead of a time of day, it's just an integer, a counter.
Exactly. When you boot up the application, your internal logical clock is at 0. When you type a letter, it ticks to 1. Type another, it ticks to 2.
So it has absolutely no relationship to the time of day.
None. It only measures causality. It proves that action number 4 happened after action number 3.
Let's run a scenario to see how this logical clock actually negotiates a conflict.
Okay.
Let's say we have Alice and Bob. They're both online looking at a shared LWW register. The current value is the word apple, and they are both synced at logical clock time 1.
Got it.
Then Bob's Wi-Fi drops. He's completely offline.
Okay, so while offline, Bob changes the value to banana. His local clock ticks to 2. Then he realizes he made a typo, changes it to berry. His clock ticks to 3.
Meanwhile, Alice is still online. She changes her value to carrot. Her clock ticks to 2.
And then Bob finally gets his Wi-Fi back and reconnects to Alice.
So Bob's computer instantly broadcasts his state over the network.
Mm-hmm.
His tuple is Bob, timestamp 3, value berry.
Right.
Alice's computer catches this broadcast. It runs the merge function. It looks at Bob's timestamp of 3. It compares it to Alice's local timestamp, which is 2. The algorithm says, hey, 3 is greater than 2. Bob's reality wins.
Right.
So Alice's computer overwrites carrot, updates its own internal clock to 3, and stores Bob's ID.
And crucially, this happens in reverse too.
What do we mean?
Bob's computer receives Alice's state of Alice, timestamp 2, carrot. Bob's computer sees that Alice's 2 is older than his 3, so Bob's computer just ignores it completely.
Oh, I see.
The conflict is resolved. Both computers now agree the value is berry, and they are both sitting at timestamp 3.
Okay, that makes sense. But I want to push back hard on the edge case here.
All right, push back.
What happens when it's a dead tie?
A tie.
Yeah. Alice and Bob are perfectly synced at timestamp 3. They both touch a totally different word at the exact same physical moment. They both tick their internal clock to 4. They fire those packets across the internet simultaneously. The timestamps are completely identical.
This is where the third element of the tuple becomes the tiebreaker, the peer ID.
So if the logical clocks are a tie, the system just compares the string of text that makes up the peer ID.
It compares them alphanumerically.
Wait, really?
Yeah. If Alice's ID is Alice and Bob's is Bob, the letter B comes after the letter A. Therefore, Bob mathematically sorts higher than Alice. Bob's state is declared the winner. Alice's update is destroyed.
I have to say, looking at that from a user experience perspective, that is deeply unsatisfying.
I know.
Are you telling me that if my name is Aaron and I'm collaborating with Zach, Zach will overwrite my hard work every single time there's a microsecond tie? I lose my data just because of the alphabet?
Yes.
That seems like a terrible way to design software.
It does feel that way.
Yeah.
But you have to separate human intent from mathematical convergence.
Okay, how?
System architects are not trying to figure out who is morally right or who deserves to have their text saved. When you are designing a distributed network, the only thing that matters is that every single peer in the network arrives at the exact same state without needing a central server to mediate.
So it's just a mechanism to break the deadlock.
Exactly. It does not matter how arbitrary the rule is. I mean, you could rule that the peer ID with the most vowels wins.
Right.
As long as the rule is deterministic, meaning every computer will independently run the exact same calculation and arrive at the exact same winner, the system achieves convergence. Bob wins, Alice's data is lost, but the document doesn't corrupt.
Which introduces a whole new vulnerability, though.
What's that?
If it's just math based on timestamps and IDs, what stops a malicious actor from exploiting it?
Oh, spoofing.
Yeah. If I know the system uses last right wins, and I really want my edits to be permanent, why don't I just hack my local client to set my logical clock to 9 million? When I broadcast my state, my timestamp of 9 million will just crush everyone else's updates for the rest of the year.
That is a very legitimate security flaw in pure client-side LWW registers. If you have a bad actor, they can easily poison the state by artificially inflating their logical clock.
So how do they stop that?
Well, in enterprise applications, this is often mitigated by having a trusted validation layer.
Yeah.
Perhaps an edge server that sanitizes logical clocks that are wildly out of bounds before passing the state to other peers.
Like a bouncer.
Exactly. But the fundamental mathematical risk remains. You are fundamentally trusting the timestamps provided by the peers.
Okay, so we've established the primitive. A single register that holds one value and uses, let's be honest, arbitrary math to break ties. But I can't build Google Docs with a single light bulb switch. A collaborative design canvas has thousands of layers, colors, text boxes, X and Y coordinates. How do you scale this atomic unit into a real application?
You scale it through composition.
Composition.
You take that simple, proven primitive, and you nest it inside larger structures. And the most common structure for this is called a last right wins map.
An LWW map. So in programming, a map is just a dictionary of key value pairs. Right?
Yes. You have a key like title and a value like Q3 strategy. You have a key called background color and a value of blue.
This is where things get slightly mind-bending for me. When you look at how a CRDT map actually stores data in memory, it doesn't just store the text Q3 strategy.
Oh, it does.
The map doesn't hold raw values at all. It actually holds a completely independent LWW register for every single key.
Right. It is entirely nested. Think of the structure of a JSON object. At the top level, you have the document. Inside that, you have a key for a rectangle. But that rectangle doesn't just have a raw width of 100 pixels.
Okay.
The key width points to an entire LWW tuple. Peer ID timestamp value 100. The key X coordinate points to its own tuple. Peer ID timestamp value 250.
It's like a corporate hierarchy. The map itself is just a middle manager.
That's a good way to look at it. Let's test that logic. How does the middle manager handle a conflict?
Okay, so the application, the CEO, comes down to the middle manager and says, hey, update the X coordinate of the rectangle to 500.
Right.
The middle manager doesn't know anything about timestamps or commutativity. The middle manager just looks at its directory, finds the specific worker responsible for the X coordinate key, and hands the data down to them.
Yes.
That worker is the LWW register. The register is the one that looks at the logical clock, compares it to the incoming update, and decides whether to overwrite the number or reject it.
That perfectly describes the delegation of logic. The map's own merge function is actually incredibly lightweight.
Because it's not doing the math.
Exactly. When your map receives a massive state update from my computer, your map just loops through all the incoming keys. If your map already has a worker for a key, say background color, it just passes my incoming tuple down to your local register to sort it out.
And if your map receives a key it's never seen before, like I just added a brand new image to the canvas, so there's a new key called image 7.
If the map doesn't recognize the key, it simply instantiates a brand new LWW register, assigns it that key, and loads it with your incoming tuple.
Wow.
The beauty of composition is that you don't have to rewrite the complex math for every new layer of the application. Because the register is mathematically proven to be commutative, associative, and idempotent, any structure you build entirely out of registers inherits those exact same guarantees.
It's elegant, but this middle manager system hides a catastrophic flaw.
Ah, yes.
And this is the part of the deep dive that really exposed the friction of distributed networks for me. What happens when we try to delete something?
The deletion problem.
Yeah, what happens when a key needs to be removed from the map entirely?
Well, deletion breaks the fundamental assumption of a distributed map.
Let's walk through the whoops scenario because it illustrates exactly why naive deletion fails.
Let's see.
Let's say Alice and Bob are collaborating on a canvas. They both have a key in their map called project name, and the value is a register holding the string secret launch.
Okay.
Bob's internet cuts out. He's offline.
Right, so while Bob is offline, Alice decides they don't need the project name on the canvas anymore. She selects it and hits delete.
Now, if the LWW map handles this naively, it just erases the key from its local directory. The key project name and its register are completely wiped from Alice's memory. Her local reality reflects the deletion.
And then Bob's internet connects.
Right. Bob reconnects, and his computer dutifully broadcasts his state to Alice. Bob's state still contains the key project name with the value secret launch. Alice's map receives Bob's state. The middle manager starts looping through Bob's keys. It sees project name. It checks its own directory.
It's not there.
Right. It says, I don't have a key called project name. This must be brand new data that Bob just created while he was offline.
Right.
So Alice's map obediently creates a new register and adds the key back into the document.
The deleted data resurrects itself.
It's a ghost. Bob never meant to recreate it. Alice explicitly tried to kill it. But because the system is designed to embrace new information, it brings the deleted data back from the dead.
Yep.
If you actually erase a key, the system has no memory that it was ever there, which means it cannot distinguish between data I intentionally deleted and brand new data I've never seen before.
Which forces engineers to adopt a very specific, somewhat counterintuitive solution.
Okay, what's the solution?
If you cannot remove data from the mat, you have to leave a warning sign. You have to use a tombstone.
A tombstone. A deeply morbid term for a data structure.
Very morbid, but highly accurate. The rule of a CRDT is that you never actually delete a key. Ever. Never. When Alice clicks the delete button on her keyboard, the LWW map does not remove the key from the directory. Instead, it accesses the internal register for that key and changes the actual value to null.
Okay, so it empties it, but it keeps the metadata.
Crucially, yes, it keeps the metadata, it keeps Alice's peer ID, and it ticks the logical clock forward to record a new timestamp.
So the state of that key becomes a tombstone. Alice, timestamp 8, null.
Exactly.
It's basically a permanent marker sitting in the system's memory that says, here lies the project name, intentionally killed by Alice at time 8.
Now run the scenario again with tombstones in place.
Okay. Alice tombstoned the key. Bob reconnects. Bob's computer sends his state. Bob, timestamp 5, secret launch.
Right.
Alice's map receives it, looks at the key, and sees it already has a worker for that key, the tombstone. It hands Bob's incoming tuple down to the register. The register compares Bob's timestamp 5 to its own timestamp 8. The tombstone's logical clock is newer, so the register completely rejects Bob's update. The value remains null. The ghost is vanquished.
And from the perspective of the application interface, the software just filters out any key with a null value, doesn't render it on the screen.
So to the user, it looks perfectly deleted.
Yes. But underneath, the tombstone remains vigilant, permanently guarding against older versions of that data returning.
Okay, I understand the logic. But if you are listening to this right now on a laptop with a bunch of Chrome tabs open, you know how precious system RAM is.
Oh, for sure.
This tombstone solution creates a terrifying reality. If we can never, ever truly delete a key, doesn't the file size just grow infinitely forever?
It does.
Wait. If I write a 100,000-word collaborative novel with a co-author, and over the course of a year we edit out 50,000 words, rewrite entire chapters, delete thousands of paragraphs, those deleted words aren't actually gone. They are all sitting in my RAM tombstoned. The document in memory is actually 150,000 words long.
In computer science terms, we call this a monotonically increasing data structure.
Monotonically increasing.
It means it can only ever accumulate mass. It can never shrink. Information is only ever added, even if that information is just a timestamp declaring that something else was deleted.
That seems entirely unsustainable. Eventually, a highly edited Figma file or Google Doc would consume all the memory on a device and crash it.
It is the ultimate friction point of CRDTs. You are trading memory efficiency for absolute network resilience. But, and this is important, Engineers don't just let the memory bloat infinitely.
Okay, what do?
They build complex mitigations to compress that history. The most prominent is garbage collection.
Wait, how can you garbage collect? You literally just said we can never remove the tombstones or the ghosts come back.
You can remove them, but it requires a coordinated compromise across the entire network.
What kind of compromise?
If the system can verify that a tombstone is incredibly old, let's say 6 months old, and it can verify that every single peer who has ever touched the document has successfully synced past that timestamp,
Oh, I see.
then the system can safely assume that the ghost data is totally gone from everyone's local hard drive. Once that consensus is reached, the system can actually prune the tombstone from the map to save space.
But consider the alternative risk there. What if a peer hasn't synced?
Yeah.
What if I collaborated on a document and then I put my laptop in a closet for a year?
Right.
The system garbage collects all the tombstones from the last 12 months to save space. Then I pull my laptop out, turn it on, and it tries to sync my year-old state.
That's the trade-off. If you reconnect after the garbage collection horizon, your old data will resurrect.
Wow.
The system will see your year-old text, realize it has no tombstones to counter it, and assume it is brand new data. Your deleted chapters will flood back into the document.
Which means garbage collection is basically just a calculated gamble on how long people stay offline.
Exactly. It's a pragmatic bet. Now the other, safer mitigation, relies on binary optimization.
Optimization of the files themselves.
Yeah. The system doesn't store these tupers as plain text JSON files, which are very heavy. It encodes the history into highly specialized, compressed binary formats.
Right.
Lazaroff notes that with rigorous encoding optimizations, the overhead of this monotonically increasing history can be squashed down to as little as 50% compared to just storing the raw current state of the document.
A 50% memory tax.
Yeah.
Honestly, if it means I never have to deal with a locked file or a corrupted server database ever again, I think most users would gladly pay a 50% RAM tax.
It is the cost of doing business in a decentralized reality.
So stepping back from all this, the LWW registers, the maps, the logical clocks, the tombstones, what is the real takeaway here? Why does diving this deep into the architecture of a text editor even matter?
I think it matters because it reveals a massive philosophical shift in how humanity is designing digital infrastructure.
How so?
Well, for the first 30 years of the internet, we believed that reliability required centralization. We believed the only way to maintain a shared truth was to appoint a dictator.
A single monolithic database.
Right. A database that held the lock, ordered the queue, and rejected anyone who spoke out of turn.
The operational transformation server.
Exactly. We tried to force the chaotic, unpredictable internet to behave like a perfectly orderly waiting room, but it's physically impossible.
Yeah.
CRDTs represent an admission of that impossibility and a brilliant pivot. Instead of trying to control the network, engineers designed a data structure that physically, mathematically cannot disagree in the long run.
By relying on commutativity, associativity, and idempotence, we removed the need for a dictator entirely.
We do.
It is a shift toward a kind of distributed, anarchic consensus.
It is anarchy secured by mathematics.
I love that phrase, anarchy secured by math.
It's the realization that we don't need to ask permission to alter our reality. It guarantees that even if we all retreat into our own isolated, offline silos, constructing wildly divergent timelines of work, the moment we reconnect, those fragmented realities will seamlessly fold back into a single, unified universe.
No conflict.
No data loss, just eventual, inevitable convergence.
Please note, this video is AI generated with Notebook LM, drawn from an interactive intro to CRDTs by Jake Lazaroff. Informational only, not advice. If you've been enjoying the journey, like and subscribe. It helps the channel grow. Thank you for watching. See you in the next one.